The first confirmed planet orbiting another sun looked like a world astronomy said could not exist. A giant planet was circling its star so quickly that it completed an entire year in just over 4 days, if that measurement was real. Decades of assumptions about how planetary systems formed would no longer fit the evidence. Yet at first, the observation lived only as a faint, repeating motion buried inside the light from a star called 51 Pegasi. Inside the dome of the 1.93-meter telescope at the Observatoire de Haute-Provence in France, the LOD spectrograph separated the starlight into thousands of narrow spectral lines. Michel and Didier Queloz were not looking for dramatic images. They were measuring tiny shifts in those lines, searching for the slight movement of a star being pulled by an unseen companion. On the computer screen, the numbers refused to stay still. Every 4.23 days, the star appeared to drift toward Earth and then away again. The movement was small, about 56 meters per second. Large enough to detect, but still small enough to distrust. Before it became a discovery, the radial velocity graph was an irritation. Each new observation landed almost exactly where the previous cycle predicted it would. The curve should have broken apart into random noise if it came from an instrumental problem or a calculation error. Instead, each added night strengthened the same smooth rhythm. Mayer and Queloz did not rush toward publication. For months, they searched for reasons to reject their own conclusion. They recalculated the mathematics. They checked the instrument. They considered whether the star itself might simply be expanding and contracting instead of responding to the gravity of an orbiting planet, announcing an impossible result, only to discover it was their own mistake, was reason enough to keep testing the signal. But the graph kept returning with the same shape, at the same interval. At first glance, it looked almost ordinary, a simple wave rising and falling across the page. Yet those plotted points carried an uncomfortable implication. If the unseen object completed an orbit every 4.23 days, then it could not be sitting several astronomical units from its star, where astronomers believed giant planets had to form. It had to be about 0.05 astronomical units away, only around 7.5 million kilometers from the star itself. Mercury circles our sun much farther away. This world was nearly 8 times closer. That distance turns the graph from an interesting measurement into a direct challenge to accepted planetary formation models. Gas giants were expected to gather their thick envelopes of hydrogen and helium far beyond the frost line, where temperatures allowed icy material to accumulate. A Jupiter-sized planet hugging its star did not fit that picture. In October, printed conference slides replaced laboratory plots as Mayer traveled to the 9th Cambridge workshop on cool stars, stellar systems, and the Sun in Florence, Italy. On October 6, 1995, the private anomaly became a public claim. The audience saw the repeating velocity curve and understood what it implied. Some questioned the calculations. Others wanted access to the raw measurements. The observation itself was clear. The conclusion was the problem. The question had moved. It was no longer whether the graph existed, but whether anyone else could make the same graph appear. Across the Atlantic, another telescope turned toward 51 Pegasi. At Lick Observatory in California, Jeff Marcy and Paul Butler pointed the Hamilton-Michel spectrograph at the same star for 4 consecutive nights. Their goal was straightforward. Either the Swiss team had made a serious mistake, or the impossible planet was real. Fresh measurements accumulated. New points appeared on another graph. They landed directly on the same sine wave. Independent observations reproduced the 4.23-day rhythm almost perfectly. The signal that had survived months of scrutiny in France now survived a different instrument on another continent. Instrumental error became harder to defend. The unseen companion remained exactly where the mathematics predicted it should be. The physical picture could no longer be set aside. The object circling 51 Pegasi possessed a minimum mass of roughly 0.47 times that of Jupiter. It was a giant planet racing around a sun-like star at blistering speed while enduring estimated temperatures above 1,000 degrees Celsius. Astronomers would eventually give this new class of worlds a name: hot Jupiters. The recurring graph changed again. It no longer represented a suspicious anomaly. It became evidence that planetary systems could evolve in ways the prevailing models had not anticipated. The consequence spread beyond a single discovery. If a giant planet could exist so close to its star, then the traditional picture of planetary formation required another process: planetary migration. The inward movement of giant worlds after their formation shifted from speculation toward necessity. Search programs that had expected to wait years for distant planets suddenly had a new target: short-period worlds that could reveal themselves within days. Observatories changed their strategies. The sky did not change. The questions did. What began as a tiny stellar wobble expanded into an entirely new field of astronomy. Thousands of exoplanets would eventually follow, but the path toward them started with one stubborn pattern that refused to disappear, no matter how many times it was checked. The radial velocity curve still survives in the published record. Its shape has not changed. Only what astronomers understood when they looked at it.